So before studying group homomorphisms in general, let me give you a couple more examples of isomorphisms. An isomorphism means a homomorphism that is also a bijection. And remember, a homomorphism from a group G to another group H is a function that respects the group operation, meaning whether you multiply two elements in G and then apply the function, or whether you apply the functions to the individual elements and then multiply them together, you get the same thing. That's this equation. So there will be one rather specific example and one rather general kind. So this is the general kind. So let G be a group and let A be an element of G. Define C sub A from G to G by C sub A of an element is you take that element, multiply by A on the left and multiply by A inverse on the right. This operation is called conjugation by A. This function has a name. It's called conjugation by A. In fact, if you give me two group elements, G and G prime, we say that they are conjugate if you can find an element, I don't know, maybe U in the group, such that this guy can be written as U times G times U inverse for some U in G. When this happens, we say G and G prime are conjugate. Now this operation, conjugation, is trivial in abelian groups, because if you are in an abelian group, you can switch the order of multiplication and then U and U inverse will just go away because they're together combined to become identity. But in non-abelian groups like permutation group or matrix groups, this operation is extremely important. In fact, in linear algebra, when you have two matrices and when you can write one matrix like CB C inverse, these matrices A and B are called similar, so you might have seen that. And they have, for example, the same eigenvalues, etc. So they have similar properties. And it's a similarity of matrices is a rather important concept. That shows that this is some important operation. So what I want to say here is that verify a bunch of things. First of all, C of the identity is the identity map of G. That's very clear. If you multiply by identity and identity inverse is also identity on left and right, you get the same thing back. Then you verify that C of one element composed with C of another element, so this is applying the functions back to back, amounts to conjugating by the product. And this is an easy verification. C of A of C of B of X is C of A of Bx B inverse, which is AB X B inverse A inverse, but B inverse A inverse is the inverse of AB, so this is just that, which is CAB X. But the second one tells you, so this is 1, 2, the second one tells you that if you conjugate by A and then conjugate by A inverse, the result is conjugating by the product, which is conjugating by identity, which is the identity map. And same in the other order. So C of A is a bijection, because I just exhibited its inverse. The inverse of this function, the inverse of conjugating by A, is conjugating by A inverse. So now that I know that it is a bijection, I just have to check that it's a homomorphism. So I have to check that C of A xy is C of A x, C of A y. With that, you can just directly verify what is the right-hand side. Maybe it's better to start with the right-hand side. CAX, CAY is AX A inverse, AY A inverse. right? This is CAX, this is CAY. But then this A inverse and A becomes identity, and then identity combines to Y to just give Y. So you just get AXY A inverse, which is CA of XY. Okay, so that's maybe a quick verification. So that tells you that CA from G to G is an isomorphism. So you have, in any non-abelian group, this would be a non-trivial map if you take an element which doesn't commute with everything. So this gives you plenty of isomorphisms. And we'll see how what these isomorphisms do in permutation group when we study permutation group in general. Okay. The second example that I want to talk about is a very specific one. Let's look at the rotational symmetries of the regular cube. We started by studying symmetries, actually rotations and reflections of the square. Let's graduate to the cube. So I'll try to draw a cube here. And so an element of this group is a rotation that you do to this cube that takes the cube to itself. And I can tell you this group has 24 things. And we can count them sort of. So what can you do to the cube? You can hold the cube using these two corners, opposite corners. Imagine a line going through this, the diagonal. Call this diagonal D1. Hold the cube along this diagonal, and if you look from the top, you'll see a tripod of the three edges coming out, these three edges. And then you can rotate by 120 degrees. So 120 degree rotation. Let's call that R1 maybe. So R1 would be an element of G. How many such elements are there? Well, there are 4 pairs of opposite corners, and for each of them you can rotate by 120 or 240. The 240 rotation across this would be R1 square. So that gives you 8 things. Or you can hold the cube using the midpoints of 2 opposite edges like this. Imagine an axis going like this. And then rotate by 180. Let me call that maybe 1R1, 2. Okay, so that's another element of G. So how many are there like that? So there are 6 pairs of opposite edges, so 6 of these. Or you can hold midpoints of opposite faces, imagine an axis going like this, and rotate by 90 or 180 or 270. So that gives you 3 pairs of opposite faces along the x, y, and z direction, and 3 rotations for each of them, so 3 times 3, 9 there. And then you have to throw in the identity, which is not doing anything at all. So that gives you 24 elements. Okay. Now what you have to check, of course, is that when you do these back to back, you do one rotation and then another of these rotations, the result is again one of these 24. But that I'll leave that to you. But I at least want to remark that you cannot quite, geometrically seeing what you get is kind of hard. I mean, if I do R1 and then I do R1, 2, I'm saying that the net result is again one of these 24. So which one is it? It requires some work. Okay. What I want to do is show you how to get a permutation of 4 letters out of each rotation. Okay. So what I'm going to do, I'm going to label the vertices of the cube like so. Call it 1, 2, 3, 4. And then the opposite vertices I'll call maybe 3 bar. Oops. What happened? 1, 2, 3, 4. That's not the opposite of 3. That's the opposite of 4. And then 1 bar, 2 bar, 3 bar. Okay. So, and then the 4 diagonals, I'll call them D1, D2, D3, D4. The 4 diagonals of the cube. And then the key observation is that each rotation in G, these 24 rotations, permutes D1 through D4. So for each rotation, I get a permutation of 4 letters. I'll show you. So example, let's do R1. That takes the diagonal D1 to D1 because I'm holding that as an axis. I'm rotating like this, right? So that diagonal doesn't change. But if you look from the top, again, you see a tripod coming out like that. And at the end, you see the vertices 2, 3, 4. So they get flipped around. So if I take the anti-clockwise rotation, you can see that this edge here, this edge goes to that edge. So the diagonal D4 is going to go to D2. And then D2 is going to go down to D3. And then D3 is going to come up to D4. Like this, like that, and then back. So that corresponds to the permutation. So R1 gives me the permutation. 1 goes to 1, 2 goes to 3, 3 goes to 4, 4 goes to 2. That's an element of S4. And then furthermore, I want you to check that composing rotations, meaning applying rotations back to back, amounts to multiplying the permutations. Believe me on this. So that tells you it's a homomorphism. And in fact, different rotations give you different permutations. So this sets up, this gives this procedure that associates to each rotation a permutation. Procedure defines an isomorphism, alpha, from our group of symmetries of the cube to S4. Alpha takes R1 to this permutation, for example. If you take our R12, the rotation across this axis, you can verify that it's going to be a flip, 1 and 2. 3 and 4 are going to go to themselves, I believe, etc. Okay. So this is a geometric creature. And this is very combinatorial. And now I can already show you how this is useful, you see, because if I wanted to multiply 2 of these rotations, compose them, it was difficult. But now if I can write down these permutations, I can just multiply the permutations very quickly. And that tells me what rotation I get when I compose 2 rotations. And this also shows you what isomorphisms are good for. So these originally looked like 2 very different kinds of groups. Now that I know they are isomorphic, what I know we'll see is that they have very same group theoretic properties. So just like 2 isomorphic vector spaces have the same vector space properties, isomorphic groups are, as abstract structures, the same. Their group theoretic properties are the same. So anything that holds for one of these groups holds for the other one too.